everyone. This is Ray Savage with Cambium Networks. Thank you for joining us for this session of Cambium College. Today we'll be talking about one of the topics that's in the news all the time these days about technology. It's MIMO and MU-MIMO, which stands for multiple in, multiple out, and multi-user multiple in, multiple out. Well, it's breaking technology. I think it's something that people would barely study even in college today, just because it's so new. And we have a very special guest speaker, one of our principal engineers here at Cambium Networks, Lucia Valbanese, who is a distinguished member of our technical engineering staff and has been deeply involved in the engineering of our PMP 450M product, which was just launched last year. Well, with no further ado, I'll turn it over to you, Lucia.
Thank you, Ray. Thank you very much. Hello, everybody. Thanks for joining us for this session of Cambium College on MIMO and MU-MIMO. So what are MIMO and MU-MIMO? You probably signed up for this session without knowing what we'll be talking about. So like Ray was saying, we'll start with the acronyms. MIMO stands for multiple input, multiple output, and MU-MIMO stands for multi-user MIMO, or multi-user, multiple input, multiple output. Is it clearer now? Probably not. First of all, what is an input and what is an output? They are defined with respect to the channel. An input is a signal transmitted from a transmitting device through a channel, and an output is a signal that travels through a channel and is received by a receiving device. To understand better what happens to a signal traveling through a channel, let's first review some of the basics of radio wave propagation. You've seen these concepts in previous sessions of Cambium College, so here we just summarize the main building blocks of a communication system. Let's assume you need to download a picture on your phone. The file containing the picture needs to be transmitted from a base station, which is the transmitter, to your device, which is the receiver. The job of the transmitter is to transform the picture into a signal that can be transmitted through the wireless channel. First, the picture is converted into bits or binary digits. These are sequences of zeros and ones that represent the colors of all the pixels in the picture. Next is the source coder. The source coder uses information on the data to be transmitted to reduce the redundancy. This step basically reduces the number of bits that are needed to represent the picture to a minimum. Next is the channel coder. The channel coder performs the opposite operation, meaning that it adds redundancy to the data. The reason is that transmitting additional bits, it's possible to correct some errors at the receiver without having to retransmit the whole signal. How much redundancy can you add? The answer is a trade-off between sending more bits that don't carry additional information and having a signal that is more robust to errors, meaning that the receiver can correct more errors if they occur during transmission. Many communication systems automatically adjust the amount of redundancy added by the channel coder based on the varying channel conditions. This means that if the channel degrades, the transmitter can add more redundancy bits and make the signal more robust. But if the channel becomes cleaner, the transmitter can reduce the redundancy and send new data instead. The next block is the modulation. Modulation is the mapping of a certain number of bits to a waveform that is transmitted over the air. The mapping between groups of bits and a waveform is unique, and the possible waveforms need to be different enough that the receiver can understand which one was sent. For example, if we map 2 bits to one waveform, we'll have one waveform for bits 0, 0, another for bits 0, 1, another for bits 1, 0, and a fourth for bits 1, 1. The modulator takes the next 2 bits in the sequence of bits that need to be sent and maps them to one of the 4 waveforms. How many bits can we map into a waveform? Again, the answer depends on the channel quality. If a channel is clean, we can map more bits into one waveform, which means that we send the bits needed to represent the picture faster. If a channel degrades, we need to map fewer bits to each waveform, and it takes more time to send all the bits that represent the picture. The last step in the transmitter is to transform the digital signal into an analog waveform and transmit the waveform through an antenna. A waveform is a signal represented by amplitude, phase, and frequency. We can see an example of two waveforms here to the right. The amplitude is how tall the signal is. The phase is a shift back and forth, and the frequency indicates how quickly the waveform repeats itself. In the picture here, we see the wavelength of the first signal. This is the distance between 2 points at the same value. For example, 2 peaks or 2 zero crossings. The wavelength is inversely proportional to the frequency. What does this mean? It means that if the frequency is low, the wavelength is large, like in the top waveform. If the frequency is high, the wavelength is small, like in the bottom waveform. At this point, the signal travels through the channel. So this is what the input to the channel is. It is the waveform generated by the transmitter carrying the bits that represent the data to be transmitted. When the waveform travels through the wireless channel, many things can happen. We'll see some examples of why the signals might degrade in the next slides. But even in perfect conditions, the signal arriving at the receiver at the minimum is attenuated, meaning that its amplitude is lower. The longer the signal travels over the air, the lower its amplitude at the receiver becomes, and the harder it is to distinguish which signal was transmitted. Another parameter that changes at the receiver is the phase. Because the waveform travels through the channel, if it started at the transmitter at the peak, it may arrive at the receiver at the zero crossing or any other point. This shift is a phase change. The signal entering the receiver is the output of the channel. So now we have seen what input and output are. Once again, an input is a signal transmitted by a device entering a channel, and an output is the signal that has traveled through the channel and is entering the receiving device. Once the attenuated and possibly distorted signal arrives at the receiver, the operations that occurred at the transmitter are reversed. First, the analog signal is received by the receiver's antenna and it is transformed into a digital signal. Then the waveform is demodulated. This means that the receiver identifies the waveform that was transmitted out of the set of possible options. In the previous example, there were 4 possible waveforms, and extracts the corresponding bits from it. The channel decoder uses the redundancy that was added to the bits to correct any errors that might have been introduced in the channel. And finally, the source decoder restores the original bits that represent the picture we downloaded. Now all the information is in the receiving device and the picture can be displayed. Now that we know what an input and an output are, let's see some options for these inputs and outputs. So next slide. Before we can talk about MIMO, which is the multiple input, multiple output, we should talk about SISO, single input, single output, but also the 2 variants in between, SIMO, which is single input, multiple output, and MISO, which is multiple input, single output. The names are fairly self-explanatory. Single means that there is only one, either a transmitter or a receiver, while multiple means there is more than one transmitter or receiver. Here the pictures show 2 antennas for the multiple case, but multiple can be much more than 2. It can be 4, 8, 16, or even more. The simplest case is SISO. There is only one transmitter and one receiver, like in the example we saw in the previous slide. The next case is SIMO, single input, multiple output. In this case, there is only one transmitter, but there are multiple antennas in the receiving device. Why is it useful to have multiple antennas or multiple receivers? The 2 or more receivers can combine the information they receive in order to have a better understanding of what was transmitted. Let's compare the transmitter to a teacher teaching a lesson, and each receiver is a student listening to the lecture and taking notes. If after the lecture the students get together and compare notes, they can make sure they didn't miss anything or clarify some concepts that were not clear. Working together and sharing information, the students all have a better understanding of what the teacher was presenting. The same is true for the multiple receivers. They can combine the received signal to create a cleaner signal. When is this scheme useful and when isn't it useful? What do we need for this scheme to work? First, let's consider the case where multiple receivers receive exactly the same signal. This will be the same as all the students taking exactly the same notes. When they compare the notes, they are all the same, so there isn't any advantage in having taken multiple copies of the notes. This is the same if the channel between the transmitter and receiver 0 is the same as the channel between the transmitter and receiver 1. If the two signals are the same, there is little advantage in having the two copies. But if the two channels are different, it's possible that one receiver missed something that the other receiver didn't, and vice versa. Now, the scheme is useful because the combination of the two signals is more complete than each of them individually. So what do we need to do to have the two channels sufficiently different from each other? One way is to physically separate the two antennas. If they are spaced far enough, the path the signal takes from the transmitter to each of the receivers is different, and the received signals will also be different. How far apart do we need to place them? How far is far enough? This depends on the wavelength and the frequency. As a rule of thumb, we want to place the antennas a wavelength apart. This means that the higher the frequency, the closer the antennas can be. But if the frequency is lower, we need to space them more to achieve the same effect. Let's now consider another aspect, which is the number of receiving antennas. Let's go back to the example of the students taking notes. Let's assume each student takes different notes, and at the end of the class, they come together to share. If two students compare their notes, it's likely that one missed something that the other didn't miss. If a third student also joins in, it's possible he or she was able to take notes on a point that both the first two students missed. But if 4, 5, 6 students compare notes, it becomes more and more unlikely that the last student can add anything new to what was already shared by all the previous students. The same is true for the multiple receivers. With two receivers, the received signal can improve significantly when the two signals are combined. But with 3, 4, 5 receivers, we start having diminishing returns, meaning that the signal might still improve, but not by much. As each additional receiver represents a cost, at one point it's not worth adding receivers if the signal is not significantly improving. This is why we don't see devices with 100 antennas. We can see 2, 4, or 8, but beyond that, you need to use different types of techniques to take advantage of the multiple antennas. Simply combining the signals doesn't give you any more improvement. The next case is MISO, multiple input, single output. In this case, there are 2 or more transmitters and only one receiver. The received signal is the sum of all the transmitted signals going through the channel. Again, if we want the signals to be different, the antennas need to be spaced enough, meaning more for low frequencies and less for high frequencies. In the next slides, we will explore each of these combinations in more details, and we'll see some ways of transmitting the two signals in a way that benefits the receiving side. The last case is MIMO, multiple input, multiple output. In this case, we have 2 or more transmitters and 2 or more receivers. This is a combination of the two previous SIMO and MISO cases. Note that here we are talking about 4 different channels because the signal transmitted by transmitter 0 travels through 2 channels and is received by the 2 receivers. These are represented by the blue arrows. Similarly, the signal transmitted by transmitter 1 travels through 2 channels and is received by 2 receivers. These are represented by the 2 orange arrows. Each receiver will therefore receive the sum of the 2 signals arriving at that receiver, one blue and one orange. In this case, we have more options available. For example, we can combine all received signals to make a cleaner signal, Or we can take advantage of the multiple transmitters and receivers and send more data instead. This is the main advantage of this configuration, because it allows to double the throughput in the 2x2 case, meaning send twice as much data in the same amount of time from the two transmitters. With the MISO scheme, you cannot send one stream of data from the first transmitter and another stream of data from the other transmitter, because with only one receiver, it is not possible to separate the two data streams. It would be like listening to two people talking to you at the same time. You cannot understand what either one is saying. But in MIMO, you have two receivers, so you can separate the data streams at the receivers and double the throughput. We'll see later how this is done. Why is MIMO an important feature and part of any wireless standard from Wi-Fi to LTE? As capacity demand increases exponentially, with more and more people downloading videos or movies, playing video games online or video conferencing, techniques that allow to send more data in the same amount of time are very valuable because you can serve more users more efficiently. So now we finally know what MIMO is. We'll now look into more details on how these techniques can be used. But first, let's take a deeper look on why a simple SISO system may not be enough. So let's go to the next slide. Now that we've seen that we can use multiple antennas, either at the transmitter or at the receiver or both, let's take a better look at what can go wrong with the SISO system and why we want to use multiple antennas. We already discussed the fact that when a signal travels from a transmitter to a receiver, its amplitude is attenuated and its phase changes. If the communication channel is not cluttered, meaning there is nothing in the vicinity of the transmitter, the receiver, and along the path between the two, we talk about line of sight transmission and free space path loss. This means that the only effect to the waveform is its attenuation and phase change. But in a real communication system, there is always some clutter. In an outdoor deployment, there will be buildings or trees or vehicles along the path between the transmitter and the receiver. In an indoor deployment, there will be walls, furniture, people. The signal that leaves the transmitter now takes multiple paths to arrive at the receiver. There might be a signal going straight from the transmitter to the receiver, but there are also additional signals that bounce off the clutter, the buildings, the trees, the cars, the furniture, and then arrive at the receiver. These additional paths have to travel a longer distance compared to the straight path. This means that they will be attenuated more compared to the straight path, and they will arrive with an additional phase delay. In some deployments, it is possible that the direct path is missing. For example, if the receiver is behind the building. In this case, we talk about non-line of sight because there is no direct path and the only signals that arrive at the receiver are the ones bouncing off the clutter. In the plot at the bottom of this slide, we see an example of an indoor signal. This could be a Wi-Fi signal propagating from the access point to a computer, for example. The signal propagates along three paths. The first is direct from the transmitter to the receiver. The second bounces off an obstruction, like a piece of furniture, and it arrives at the receiver later than the direct signal because it travels a longer distance. The third bounces off the ceiling, and it arrives even later, as the path it travels is the longest. To the right, we can see the three received signals. The red one is the one arriving first and is the strongest. This is the direct path. The purple one is the one bouncing off the obstruction, and it arrives later with a smaller amplitude. Finally, the blue one is the one bouncing off the ceiling, and it arrives even later and with the smallest amplitude. The signal that enters the receiver is the sum of all these signals, and it is represented at the bottom as a combined result. You can see how this signal is distorted compared to the direct signal, the red one. Imagine how more and more of these additional multiple paths are arriving at the receiver. Each one of them distorts the signal even more, and it makes it harder and harder for the receiver to detect what signal was transmitted. There are also some cases where the signal is not just distorted, but it could be completely or almost completely canceled. This is what we call fading. So let's go to the next slide. To understand the mechanism of fading, let's consider only two signals arriving at the receiver. Let's assume these two signals arrive with the same amplitude, which means that they travel the same distance from the transmitter to the receiver. This scenario occurs, for example, if you don't have a direct signal and two paths bounce off two obstacles to the left and to the right of the receiver, traveling the same distance to the receiver. In the first case here, the signals arrive in phase. This means that they have the same zero crossings and the same peaks. Essentially, the two signals are the same. When they enter the receiver, they are added together. The sum of the two will be a similar signal with an amplitude twice as big. As bigger signals are easier to detect at the receiver, the interference or sum of the two signals is called constructive, because the resulting signal is stronger than the two individual signals, and the receiver can receive it better. In the second case, they arrive 180 degrees out of phase. What does this mean? It means that when one has a positive peak, the other has a negative peak, and they have the same zero crossings. So one is an upside down flip version of the other. When the two signals enter the receiver, they are added. As each positive part of one signal is aligned to the negative part of the other signal, the sum is zero. This interference or sum of the two signals is called destructive because the resulting signal is completely wiped out and the receiver cannot detect what was transmitted. You probably have experienced fading if you listen to the radio while driving. It can happen that you stop in one location and you hear only static noise on the radio. But if you move just a little, you now hear the music clearly. This happens because the first location is where the signals add up destructively. The combined signal is so small, you only hear the static noise in the background. But moving just a little shifts the phase of the signals, and now they add up constructively. This example of constructive and destructive interference is a simplified version with only two signals. But in a real communication channel with a large number of signals adding at the receiver, the effect is similar. Sometimes the signals add up constructively and sometimes they add up destructively. This effect happens in space, in time, and in frequency. In space is what we discussed in the example with the car moving slightly and having a very different reception quality from the radio. It means that in one location the combined signal is strong and in another location it is weak. But the effect of fading can also happen in one fixed location over time. If the clutter around the receiver moves, for example, cars or people move, the multiple paths change over time, and sometimes they add constructively and sometimes they add destructively. We see an example of this in the top right plot. This is a plot of the received signal power in dB. dB, or decibels, is a relative measure of the signal strength. Think of the 0 dB level, the signal strength of the direct path alone, without any other path arriving at the receiver. You can see from the plot that sometimes the level is above 0, which means that the signals added constructively and the resulting signal is stronger, and sometimes the level is below 0, which means that the signals added destructively and the resulting signal is weaker. You can see how sometimes the signal is very, very weak. The values in the plot that have a large negative value are called deep fades, because the signal can barely be detected when it is this weak. A similar effect can also happen in frequency. We have discussed how each waveform has a frequency, which is related to how fast the signal repeats itself. As signals at different frequencies are attenuated differently, when they propagate through the channel and they arrive at the receiver, they can add constructively or destructively. This means that some frequencies can be received easily at the receiver, but other frequencies show deep fades and are not easily received. Because of all this, we can see how a single signal may or may not be received correctly at the receiver. This is why we want to add transmitters or receivers or both to increase the probability of receiving the signal correctly. Let's go to the next slide. In light of this discussion on what happens in the communication channel, let's revisit the options we have introduced earlier, starting from the SIMO case, the single input multiple output. This is also called the receiver diversity because the different copies received by the multiple receivers can be combined to make a better received signal. In this plot, we see an example of a system with 2 receive antennas, and the signal strength at each antenna is shown in the plot in the blue and in the red lines. As discussed before, the channel has some good reception spots and some deep fades. But if the antennas are uncorrelated, meaning that they are far enough from each other, and the channels the signals travel through are different, the fades of one antenna will not line up with the fades of the other. This is the example we discussed earlier of students comparing notes and checking if one student missed a note and another one didn't. With multiple receive antennas, it's the same concept. One antenna can receive a good signal while the other is in a deep fade. How can we take advantage of these multiple signals? There are different options that can be used. Some options are more complex than others, and typically the most complex give the better performance. The first option is a switching technique. In this case, only one antenna receives the signal. As long as the received signal stays above a predetermined threshold, this antenna keeps receiving the signal. As soon as the signal strength dips below the threshold, the system switches to using the second antenna. If the signal of the second antenna is above the threshold, the system keeps using the second antenna. And again, when it dips below the threshold, it switches again. This technique can be used with any number of antennas, and it's simple and not expensive because there is only one receiver connected to one of the antennas. However, it's not optimal because it's possible that the signal from antenna 1 is above the threshold and is used by the receiver, but the signal from antenna 2 would have been even stronger and therefore better. The advantage, though, is that the deep fades are eliminated because they would be below the threshold, and in that case, the signal from another antenna is used. A more complex but better solution is selection. With this technique, the device measures the received signal strength from each of the antennas, and it selects the antenna with the strongest signal. In the figure in this slide, the system would select the red line every time it's above the blue line, and the blue line every time it's above the red line. You can see how the deep fades are again eliminated, but now the signal used is always the stronger of the two. This technique is better than the simple switching, but what happens if both signals are approximately the same? The selection technique will use one or the other, but eliminating the weaker of the two, it eliminates valuable information. A more complex technique is the combining technique, which uses all the received signals and combines them. In this way, all information is used and no received signal is discarded. How can we combine the signals? A simple way is to use an equal gain. For example, we simply average the signals. This reduces the effect of the noise. A better way is to use different gains, meaning give a higher weight or gain to the stronger signals and a lower weight or gain to the weaker signals. This technique is called maximum ratio combining, and it gives the best results at the expense of being more complex. Let's move on to the next slide. The other configuration we had mentioned was MISO, multiple input, single output. In this case, we have 2 or more transmitters and only one receiver. How can we make the received signal more robust in this case? First of all, we have to consider how many transmitters we want to have. If you have a certain amount of power available in the device, this power has to be divided among the transmitters. The more transmitters we have, the less power each one will be able to transmit. The second consideration is that we don't want to send the exact same signal from all antennas. If we do, what happens? This is the same case of constructive and destructive interference we just discussed. If the signals are the same, but traveling through the two channels, they arrive with opposite phases, they could cancel out. This, of course, is not desirable, as you were better off without the second transmitter. So we know we cannot send the same signal. Then what can we send? MISO systems operate differently depending if they have information on the channel or not. This is called channel state information. If the transmitter does not know the characteristics of the propagation channel, we talk about open loop systems. In this case, the transmitter needs to make decisions regardless of the specific characteristics of the channel. If the transmitter knows the characteristics of the propagation channel, we talk about closed loop systems. In this case, the transmitter can make better choices because it knows what is going to happen through the channel. Which one is better? Well, of course, the closed loop will give you a better performance, but it is more complex because you need to close the loop, meaning receive information on the channel. Let's first look at the open loop case. If you did send the same signal from both antennas, which we know we don't want to, you would send the symbol or waveform S0 first from both antennas, then S1, then S2, and so on. Now, we said we don't want to send the same signal. So we are going to send symbol or waveform S0 from the first antenna and symbol or waveform S1 from the second antenna. At the receiver, the received signal is the sum of the two, so S0 plus S1. Can the receiver distinguish between the two? We said this is like having two people talking to you at the same time. You cannot follow either conversation. So how do we fix this? After having sent S0 and S1 from the two antennas, we then send the negative of S1 from the first antenna and S0 from the second antenna. The negative is used to make the math at the receiver easier. There is also a complex conjugate component here, which we can ignore for the moment, which is also used to make the math easier at the receiver. The important concept here is that we repeat the same two waveforms, but swapping the antenna they are transmitted from. Why do we do this? Well, if the channel between the first antenna and the receiver is temporarily better, then each of the two signals has a chance to be sent through that. Remember that in this case, we don't have channel state information, so we don't know which one is better. The only option is then to try both. At the receiver, during the second transmission, the received signal is S0 minus S1. So we have received first S0 plus S1, and then S0 minus S1. We now have two equations in two unknowns, which means we have enough information to separate the two signals. Note that we have not increased the throughput in this case. It is true that in the first transmission we sent both S0 and S1, so two waveforms instead of one, but in the second transmission we have repeated the same two. We use two transmissions for two waveforms, which is the same speed we were using in SISO systems. However, we have transmitted each signal through two different channels, and therefore we have increased the probability of a clean signal to be received at the receiver. This technique is called space-time coding. Let's now look at the closed loop case. First, to close the loop, we need to know what the channel is. We have two options here. The first is used in systems that use the same frequency in both directions. One direction, called the downlink, is from the access point or base station to your device. The other direction, called the uplink, is from your device to the access point or base station. If the two directions use the same frequency, the channel is the same going one way or the other. Each receiver can then estimate the channel at its end and assume the other device sees the same channel. This is a simple method and can work well, but if you have an interfering source, for example, close to one end but not the other, then the channel seen at the two ends is no longer the same. The second method does not make any assumptions and just measures the channel. In this case, a known signal is sent from the transmitter to the receiver. The receiver then sends back the information of what was received. So the transmitter knows both what was sent and what was received. In this way, it knows what happened during transmission through the channel. If you do know what happens to the signal through the channel, you can use more efficient techniques. For example, if the transmitting device knows which channel is better, it can switch to using it and concentrating all the power in one path instead of splitting the power. What we have discussed so far is typically implemented with a small number of antennas. If you have a much larger number of antennas at the transmitter or receiver, you can use smart antenna techniques that achieve even better performance. Let's see them in the next slide. Beamforming and beamsteering are two techniques that improve the signal quality by using a large number of antennas, either at the transmitter or at the receiver. By large number, we mean at least 4 or 8 or more. The concepts behind it are similar to what we have discussed so far, but with more antennas, better performance can be achieved. Let's start with beamforming. In this case, we have a large number of antennas at the transmitter, but only one at the receiver. Assume that the transmitter knows the channel. For example, it knows the phase of the signal arriving at the receiver when it is transmitted from each of the antennas. If we know that the phase will be shifted by a certain amount, we can shift back the transmitted signal by the same amount so that it reaches the receiver with no shift. If this is done for each transmitted signal, each shifted back by the shift it would have at the receiver, then all signals arrive exactly with the same phase at the receiver. This guarantees that the signals are always added constructively, and the resulting signal is the sum of all, or the product of the signal and the number of antennas. This means that if we have 4 antennas, for example, the received signal will be 4 times stronger than if it was transmitted by 1 antenna only. If you want to visualize this mechanism, we can imagine the signal propagating from the transmitter being squeezed in one direction only, towards the direction of the receiver. We can see this effect in the picture in this slide, where the beam generated by the transmitter points toward the location of the receiver. For this method to be effective, we need to know where the receiver is, or alternatively, what the channel looks like. Assume a point-to-multipoint scenario, where one access point talks to multiple devices. The access point has the channel state information for each device. When talking to device 1, it will use the channel information for device 1 and point the beam towards that device. Then, if it needs to send data to device 2, it will use the channel information for device 2 and point the beam towards device 2, and so on. This mechanism has 2 important advantages. First, as the power is concentrated in one direction only, the received signal is stronger, and the receiver has a higher probability of receiving it correctly. Second, because energy is only going into one direction, this transmission creates less interference for other devices that could be in the same general area and operating at the same frequency. Only the devices in the same direction as the receiver will hear the transmission, while all other devices will not receive any interference. In addition to point the beam in the direction of the receiver, beamforming can also be used to point the null of the antenna pattern in the direction of other devices that are not supposed to receive the transmission. This means that not only we can control the phase shifts so that the signals add up constructively in one direction, but we can also control them so they add up destructively in another direction. This is true both if you are transmitting or receiving. When we use multiple antennas at the receiver in this type of configuration, we talk about beam steering. Essentially, the beam steering receiver shifts the received signals according to the shift that occurred in the propagation channel to align all the signals so that they add up constructively. This is the same as steering the beam towards the desired user. At the same time, the shifts can also be selected to steer the null in the direction of other interfering users. This means that signals coming from other directions will add destructively and will not interfere with the desired signal in the main beam. Switching the phases at the transmitter and receiver is fast, and each transmission or reception can point in a different direction depending on the device that is scheduled to send or receive the data. Now that we've seen all these advantages of having multiple antennas, let's ask ourselves, in which devices do we want to use them? Of course, a device with many antennas is bigger and more expensive. Let's consider again the case of a point-to-multipoint link, such as a base station communicating with multiple cell phones, or a Wi-Fi access point communicating with multiple computers. In both cases, it makes more sense to put more cost and complexity on the access point or base station side. We want our devices to be as cheap as possible, and adding antennas makes them bulky, more expensive, and also they would use more power, which is undesirable with mobile devices. If we have more antennas on the base station or access point, in the downlink direction, the one from the base station to the cell phone, or from the Wi-Fi access point to your laptop, we can use transmit diversity techniques or beamforming. On the other side, the uplink direction, the one from the cell phone to the base station, or from your laptop to the Wi-Fi access point, we can use receive diversity or beam steering. If you happen to have a device with multiple antennas as well, then you can combine advantages of transmit and receive diversity. This is the case we call MIMO, or multiple input, multiple output. Let's see this in the next slide. So let's put all we've seen so far together. If we combine the SIMO and MISO concepts, we have MIMO, which is multiple input, multiple output. In this case, we have multiple transmitters and multiple receivers. We now have more flexibility. In both MISO and SIMO, we've seen how diversity can be used to receive a stronger signal. But having multiple antennas at both sides also gives the option of increasing the throughput. Let's start with the first case. If we want to make the system more robust, we can use transmit diversity to send a single stream of data. For example, we can use space-time coding to send waveforms from each antenna, as we saw before. The advantage now is that we also have two receivers, so the signals received by the two receivers can also be combined using a switching technique, selection, or combining, as we saw for the SIMO systems, to make the received signal more robust. But a MIMO system can also be used to send more data. Imagine that in the first transmission you send waveform S0 from one antenna and S1 from the other. But in the second transmission you now send waveforms S2 and S3. You now have sent 4 waveforms in 2 transmissions, so you have doubled your throughput. This means that the video you are downloading will take half the time, or that one access point can serve 2 devices at the same time without slowing down anybody. At the receiver, each of the antennas receives the sum of the transmitted signals, but because we have 2 copies, because there are 2 receivers, we can separate them. Again, the trick is that the channels have to be different enough. As we said before, we can space the antennas enough, or in this case, we can also take advantage of polarization diversity. This means that we can have one pair of antennas installed vertically and the other pair of antennas installed horizontally. By pair of antennas, I mean one transmitter and one receiver. So the vertical transmitter can send a stream of data to the vertical receiver, and the horizontal transmitter can send a stream of data to the horizontal receiver. We now have 2 parallel streams of data, which is similar to having 2 separate radios. Are the signals completely separate? Well, you can always have some crosstalk between the horizontal and the vertical paths, but having the 2 antennas connected to the same radio, you can clean up the signal internally, meaning that you can separate any residual interference. As we discussed in the MISO system, different choices can be made depending on the presence or absence of channel state information. If the transmitter does not have channel state information, it needs to make generic choices. So it will, for example, split the power equally among the transmitters. But if it knows which transmitters is a better channel, it can allocate power in a smarter way, according to which channel is cleaner. Let's move on to the next slide. So to summarize what we've seen so far, we talked about SISO, SIMO, MISO, and MIMO systems. All these systems have in common the fact that the communication is between one access point and one device. If the access point or the device or both have multiple antennas, we can either receive a stronger signal or send more data, but the destination of the transmission is always one single device. We have talked about transmitting a dual stream or two streams. The two streams are really two parts of the same transmission, and they have the same destination. Let's consider a point-to-multipoint case where an access point is connected to multiple devices. What happens if many devices request data at the same time? For example, one user can be downloading a document, another can be watching a video, another can be video chatting. Because the access point can send data to only one device at a time, it uses what is called time division duplex, which means that the devices will have to take turns over time, as only one at a time can communicate with the access point. The process to decide which device receives data is called scheduling. Let's talk about scheduling for a moment before continuing with MU-MIMO. The scheduler runs in the access point or base station, and it decides which device receives data when and for how long. The scheduler needs to make continuous decisions based on many parameters. For example, if one user is making a voice over IP call, it doesn't need to send or receive a lot of data as voice packets are small, but they are time sensitive and they need to be sent and received as soon as they are ready. If there is a delay in the transmission, it will be noticeable during the phone call as one person speaks, but the information is not received by the other person. These transmissions cannot tolerate latency and need to be sent with higher priority. Another example of high priority traffic is online gaming. If you are playing a game, but the command is not sent, obviously the gaming experience is degraded. On the other hand, there are types of traffic that are more tolerant to latency. For example, if you are downloading a file or checking an email, you can tolerate some extra time to complete the download. This type of traffic is sent at lower priority, meaning after the higher priority traffic has been sent. This is just an example of the decisions the scheduler needs to make, but things are not that simple. If the access point sent all high priority data first, and then all low priority data, we can imagine a scenario where there is so much high priority data that the low priority data cannot be sent. In order to avoid this, the scheduler needs to make sure some low priority data is also sent. Of course, there could be more than two levels of priority, and there could also be priority among users. For example, if one user paid more for his plan, his data can be prioritized versus another user that paid less. Additionally, systems that support mobility also take into consideration the quality of the link between the base station and each user. As a mobile user will be in good and bad spots over time, the scheduler will try to prioritize the users that are in good spots first, so they can receive their data fast and correctly, waiting for the others to move to better spots. Regardless of the specific algorithm the scheduler uses, it can still just send data to one user and then move on to another one and then another one. Let's now go back to the multiple antenna case and see how it ties with the scheduler options. When we talked about beamforming, we discussed how multiple antennas can work together to form a narrower beam pointed toward the device that is receiving the data. Now imagine that the multiple antennas, instead of creating one narrow beam, create multiple narrow beams, each pointed towards one of the users. In this case, the access point can transmit multiple streams of data to multiple devices, and the transmissions don't interfere with each other. This is what we call MU-MIMO or multiple user MIMO, because multiple transmissions go to multiple users at the same time. In this case, not only we have increased the throughput, but we can send different data to different users. In the previous example, where we had one user downloading a document, another watching a video, another video chatting, Instead of sending data to one at a time, the access point can now send data to all three of them at the same time. This means that the scheduler allocates resources, meaning transmission time, to all three at the same time. How is this possible? Imagine you have multiple streams of data to send. For each of the antennas, each of the streams of data are multiplied by an amplitude and a phase component and added together. This means that stream 1 is multiplied by an amplitude factor and shifted in phase. Stream 2 is multiplied by another factor and shifted in phase, and so on. Then all the streams are added together and sent through antenna 1. The same process happens for the other antennas, but now the amplitude and phase components used to multiply the streams are different. Each antenna has its own set of what we call weights, which are the amplitude and phase to apply to each stream. If you select these weights correctly, you can create multiple beams, each in the direction of one of the users. Additionally, you can create nulls in the direction of the other users. For example, here we see a pattern with 3 beams with 3 different colors to indicate that they carry data to 3 different users. The red beam has its peak in the direction of user 1. The blue beam has its peak in the direction of user 2, and the green beam has its peak in the direction of user 3. What may be less obvious is that the red beam also has nulls, meaning very deep attenuated values, in the directions of users 2 and 3. Similarly, the blue beam has nulls in the directions of users 1 and 3, and the green beam has nulls in the direction of users 1 and 2. This means that the data that, for example, the blue beam sends to user 2 is deeply attenuated in the direction of users 1 and 3. Users 1 and 3 are, however, in the direction of the beam carrying their own data, which can be received without significant interference from the other beams. So the first thing to remember about MU-MIMO is that we do not have one antenna talking to one user, another antenna talking to another user, and so on. All antennas talk to all users, but the data is multiplied by weights that make it readable only in the location of the desired user. How many users can an access point talk to at the same time? That depends on how many antennas we have with the same polarity at the access point. For example, if the access point has 8 vertical antennas and each of the receiving devices has 1 vertical antenna, then the access point can talk to 8 devices at the same time. However, if the 8 antennas are 4 vertical and 4 horizontal, and the receiving device has 1 vertical and 1 horizontal antenna, then the access point can talk to 4 devices, sending 2 streams, 1 vertical and 1 horizontal, to each of them. What happens if you don't have data to send to all 8 or 4 at the same time? You can always send data to fewer users, and each signal will be cleaner. Let's think again about the nulls in the direction of the other users. The nulls can be very deep, but the transmission will never be completely eliminated. This is why we say there is a residual error, which means that the multiple beams are not completely separated and they slightly interfere with each other. This interference is small, but if one of the beams is not generated because there was no data to send to that user, it would be even smaller. Looking at the example with the 3 beams in this picture, if the second user has no data to receive, only the red and the green beams are generated. The nulls of the red beam are in the direction of the green beam, but they introduce a small interference. As the blue beam is not there, there is no additional interference, and the signal going to user 3, the green beam, is cleaner than when user 2 had data. This means that there are advantages in every situation. If there is data to send to all 3, then the overall sector throughput is higher, as 3 devices receive data at the same time. But each transmission is a little noisier compared to the case where the others are not present. If there is no data to send to some users, the ones that do receive data will receive a cleaner signal, as there is less residual interference. This is why we say that a device with 8 antennas, for example, can communicate with up to 8 users. If fewer need data, fewer can be scheduled. We said that the creation of these peaks and nulls is done by multiplying the streams by weights before they are added and sent through the antennas. The weights is where the magic resides. They are the ones that point the beam and steer a null. But how are they calculated? The way to calculate the weights is to know the channel state information. The access point needs to know the characteristics of the channel between itself and each of the devices. This includes knowing the location of the device so that it knows how to steer the beams and the nulls in the right directions. In order to know the channel, the access point performs a procedure called sounding with each device. Essentially, this means that the access point sends a known transmission, and each device will report back exactly what was received. By knowing what is transmitted and what the receiver received, the access point can calculate the channel. This process has to be repeated periodically. If a device is mobile, sounding has to be done often to keep up with the movement of the device. But even in fixed deployments, the channel could be slowly changing. For example, if there is movement around the device and the multipath changes. Performing periodic sounding, the access point has constant visibility of what the channel is and can calculate the weights accordingly. We talked about the fact that the access point can send data to multiple users or group multiple users in the same transmission. But can any user be grouped with any other user? Or are there some restrictions the scheduler needs to follow when forming groups? Let's imagine that user 2, the one in the blue beam, is very close to user 1, the one in the red beam. In order for the access point to send data to both, the two beams, the red beam and the blue beam, must be very close to each other, almost overlapping. If the beams point in the same direction, we can no longer have the nulls in the direction of the other user. What happens is that user 1 can also hear the transmission sent to user 2, and user 2 can hear the transmission sent to user 1. This means that the two transmissions interfere with each other and the data is lost. So we understand that two users cannot be too close to each other. Let's look at an example of a sector with a large number of users so we can see what the rules are. Let's go to the next slide. In this plot, we see a large number of users in a sector served by one access point. The red and green users are an example of two groups that can be formed. For each of the two groups, the users are spaced enough, meaning that their location in azimuth is far enough that when the access point forms the beams, they're sufficiently spaced and not overlapping. However, if we see one of the red users and the green user next to it, these two could not be part of the same group, as they are too close and their beams would overlap. They have to be part of two different groups. Depending on parameters such as the number of antennas, the spacing of the antennas, the frequency used by the access point, there is a minimum separation that users need to have in order to be grouped. So what does the MU-MIMO scheduler need to worry about? Every time the scheduler needs to make a decision on which user can receive data and for how long, it needs to check, first of all, which users have data waiting to be sent. If at one particular instant one user is not active, no data needs to be sent to that user, and it is excluded by the selection algorithm. Then it needs to consider the priority of the data to send. Is this data that needs to be sent right away, or can it wait? Then the priority of the user itself. Did this user pay more for a more expensive plan and needs data faster? Then the location of the users requesting data. Are the users spaced enough they can be part of the same group, or do multiple groups need to be formed? And also the amount of data to send to each user. For example, if one user is downloading a movie and another is only receiving a short packet, it may not be worth going through the calculations for the weights in order to group these two users if one transmission takes very little time. It may be better if the user that is downloading a movie can be grouped with a different user who is also downloading a large file, so the two transmissions can be grouped for a longer time. After the scheduler has selected the users to group, the math calculations start. The access point is to access the channel state information of all users in the group, which we said needs to be periodically updated through sounding, and calculate the weights to apply to each stream going through each antenna. These weights are valid only for transmission to this group. The next time a new group is formed, it will have different users with their own channel, and new weights need to be calculated. We already mentioned that the maximum number of users that can be grouped is limited by the number of antennas. If you have 4 antennas, you cannot send data to 5 users. 4 is the maximum you can have, if all antennas have the same polarities. If the scheduler didn't find enough users to group, for example, not many users were active at the same time, or the ones that were active were too close to each other and could not be grouped, the group can still be formed with fewer users. We already mentioned that having fewer beams, there is less residual interference, and the transmissions to the users have a higher probability of being received correctly. So this ends our presentation on MIMO and MU-MIMO systems today. If you have any questions, please go ahead and you can ask them.
Well, thank you, Lucia. Right now, there are no questions in the queue. So what we will do is actually post the recording to the Cambium community, and also I'll post a copy of the PDF of the slides that you did. Thank you very much. In addition, what I'd like everybody to do is just understand that certainly there's a lot of deep theory here, but I'd encourage you to go take a look at the PMP 450 web page, and you can see that there's a number of case studies there where customers have actually deployed this technology and have got really astounding results as far as the number of subscribers they can connect to one radio and the throughput that they can support at any given time. So thank you very much, Lucia. And let's see. Okay, first off, we do have 2 comments for you. I would certainly like to say my thanks, but one listener says, thank you very much for the informative presentation. And wow, that was very in-depth and very well prepared. Thank you for a great presentation. Thank you, Lucia, and we look forward to seeing everybody on the community. Thanks very much, everyone.
Thank you, Ray. Thanks, everybody. Bye.